probably a pretty familiar sound, just the sound of a fire truck going down the street. You may have noticed something interesting happen about halfway through there. The frequency of the fire truck changed. Now, nothing happened with the siren. There was no change. It didn't decide to, I'm getting tired of this frequency, let's try a different frequency. It all has to do with the observer. So if you were listening to this at a particular point on the street, and the fire truck was passing you, and your friend was further down the street, and the fire truck continued towards them, they would hear this original frequency. They would hear that frequency the entire time. Now, you could tell here when the fire truck passes you, partly because it's when it's the loudest, but mostly because the frequency will abruptly change and become quite a bit lower. And this is all due to something called the Doppler effect. Now, you've probably heard of the Doppler effect back in grade 9 when looking at the Big Bang Theory, because the Doppler effect doesn't just work for sound waves, it works for all waves, including light waves. Now, light waves have to be traveling, the sources have to be traveling a lot faster in order to see this with light, but we are managing to hear it in a fire truck. So let's look at how this works. I'll get rid of this thing. When a stationary object emits sound, the waves just go away from where the object is emitting. So you get these nice concentric circles like we've drawn there. The circles, each line in a circle represent what we call a wave front. A wave front is a kind of a graphical representation of all the points in a wave that are the same point, like say all crests or all troughs. I like to use crests, doesn't really matter what you use. But essentially, the way that it works then, if it's the distance from a crest to a crest, so let's say this point on the wave represents a crest, this point on the wave represents another crest, which means this is a wavelength. And if you'll notice, this is not drawn perfectly, but it's pretty close. That is a wavelength as well. From the center to this point over here would be the same wavelength. All of these wavelengths would be exactly the same. So it doesn't matter if you're standing over here and observing this wave coming towards you that way, or if you're standing over here and observing the wave coming towards you that way, or if you're standing over here. It makes no difference where you're standing because the source is not moving. So all the wavelengths are exactly the same. If the wavelengths are exactly the same, then it means the frequency is exactly the same. However, let's consider what happens when we have a moving source. Let's back up here a little bit. We'll see our end product. So if we have a source, and that source is emitting a wave, and one period later, let's say that's where our source is. One period later, the wave will have expanded to be exactly one wavelength away. So from the blue dot to the middle to where the wavefront is, that's one wavelength after one period. After another period, this thing is going to approximately double in size. So we'll say something like that, and would be right out here. But since we have a moving source, let's say our source is moving to the right. Since we have a moving source, that's where the source was originally, so we'll call that point 1. A little while later, our source is, let's say it's going to be right here. So the wave that is being produced by the source now has moved. So let me draw a little circle about that size. Go back. So we'll say right about there. So now this circle will be expanding from the point where it was created, which is right over there. You could probably already see a pattern. Let's extend it to a third period here. So let's make this bigger again by a little bit. So I'll say like that. And it should still be centered at point 1. This one gets bigger as well. And again, that one should be centered somewhere at point 2. And let's look at a third spot right over here. That's number 3, and there's going to be another circle being created. Let's say like that. There we go. And that's centered over here. So we can definitely see a pattern that's developing here. So the wavelengths are no longer, and I'm going to draw the wavelengths in green here, the wavelengths are no longer the same. You have a certain wavelength over here, and if drawn perfectly, that should be the same as the wavelength that you would get over here. This wavelength is different as well. That one is, this wavelength over here is different. That wavelength is way different. That wavelength is different. So the observations that you make for a person sitting over here, the wavelength is going to be different than a person that's sitting over here observing this wave or a person observing over here. Since the source is coming towards the person on the right, we say that the source is approaching. So we're going to use the letter A to represent all things when the source is approaching. Here, we use the word receding. So we're going to use a letter R to represent all things receding. So this wavelength could be considered lambda R. This wavelength could be considered lambda A. So we notice a trend. The wavelengths appear to be larger in the direction that the source is receding. So moving away from. And they appear to be smaller in the direction that the source is approaching. So in summary, when the object is approaching, lambda is getting smaller. So the frequency, based on the wave equation, the speed of the wave is the same in both cases because it's still traveling in air, and the speed in air is only dependent on the temperature. So the speed of the wave stays the same. So if v is the same and lambda is lower, then f is getting higher, so a higher pitch. So when something is moving towards you, the pitch is actually higher than it would normally be if it was just standing still. When the object is receding, then lambda is getting larger. So the frequency is getting lower. So in the approaching case, the frequency is higher than it would normally be if it was standing still. In the receding case, the frequency is lower than it would be if it was standing still. So the effect is even more noticeable because it goes from too high to too low. At no point in time is it normal. It goes immediately, once it passes you from, it goes immediately from approaching to receding. So let's look at how this works. I'll start over again here because this is a bit, probably the most complicated derivation that we have done so far in this course. It may be the most complicated derivation that we do in this course. So bear with me here. Okay, we're going to come up with a formula to use to determine what frequency we actually hear, what frequency we would detect, whether the object is coming towards you or away from you, based on the actual frequency of the object if it was standing still and how fast the source is moving. So the diagrams on the right represent a source moving towards the left. So let's label this here as lambda A, the wavelength of the object, of the sound as it is approaching an observer, and this would then be lambda R, the wavelength of the sound as it is receding, as the source is receding from an observer. So lambda A is the wavelength observed when the source is approaching, and lambda R is all the same stuff, but when the source is receding. A couple of more terms that we need to know. First of all, let's look at the idea of lambda naught, or lambda 0, or the original wavelength, and that is the wavelength let's try that again. Wavelength when the source is stationary. So if the thing wasn't moving, what wavelength would the sound have in air? A couple of speeds we need to talk about now, and here's where you need to pay particular attention. V is going to represent the speed of the wave. So there's two speeds here. The other speed that we're talking about is going to be called Vs, and that is the speed of the source. A lot of people will get this Vs confused with the speed of sound, because let's face it, that's what that wave is. It's the speed of sound in air. So you will have to do some questions. You will have to become experienced with the equation once we develop it, in order to remember that V is the speed of the wave and Vs is the speed of the source. You do have this equation on your equation sheet, but if you get these two concepts mixed up, the equation isn't going to do you any good. You're going to get answers that don't make any sense. A couple of other terms that that will come along as we go through the derivation. T is the period of the source. The waves are being, regardless of whether it's moving or stationary, the waves are being generated at a certain frequency. Right? That is the frequency. That frequency is based on the sound, how the sound is being produced. And so let's look at it this way. Let's consider what happens when the source is approaching, and then we'll come back and see how this would be different if the source was receding. So for an approaching source, so let's look at the distance traveled by the source in one period. In one period. So think about one period. Let's go back up to the diagram here. So our original position is right at the center of the big circle. Our next position is moved over a little bit. Our third position is moved over a bit from there. So my circles aren't spaced out perfectly. But you can see that there's a movement. This distance from there to there is how far the wave, or the object, travels in one wavelength, or in one period, I should say. So here's our object. It emits a wave. A little while later, the object is, we'll say here's our object at the center of that circle. A little while later, the object is here, and it's just starting, we'll say, to emit another wave. So this distance that the object travels, we know that d is equal to v times t. Well, the object is traveling at Vs, that's the speed of the source, and it's doing that for, we said, for one period, so the time is t. So that's how far the object travels. That's d. If we look at this diagram, the wavelength is the actual wavelength being produced from the source, we'll say from right there to right here, that is the original wavelength. So forget about the second wave. Just look at the first wave. The first wave is produced when the object is at point 1 here, and the wave will spread out, and this is one period later. This is how far right here, that's how far the wave has gone. So that's one wavelength, as if it was not moving. So that's lambda naught, lambda 0. This is where the next wave is being produced, kind of right over top of position 2, where the object is after one wavelength. So from here, the distance, I'll draw it in green as well, from there to there, that is the wavelength observed based on the fact that it is approaching. So the distance between crests would be from this point right there to this point right there. Remember, the whole reason that the wavelength is decreasing, the apparent wavelength is decreasing, or the approaching wavelength, is that the object is moving towards the direction that the wave is moving. So when at position 1, when the wave was generated, the wave started to move out at a certain speed, but the object was essentially following it. So the object was moving towards where that wave was moving, and then it started to emit another wave. So imagine it kind of like you throw a baseball at a certain speed, but then you run after the baseball, and then you throw another baseball. So if you're throwing both baseballs at the same speed, those two baseballs are going to be closer together than if you had just stood in the same spot and started chucking baseballs. So that lambda A is what we're really interested in. Now, if we look at all of this together, we have lambda naught, we have lambda A, and we have from here to there is D. So based on that diagram, now just to be clear here, the wavelength, the wavefront that I've drawn at position 2, I've drawn it around that dot. It really should be completely overlapping it, but obviously if I try to draw a diagram where it's completely overlapping, it would just look like another dot. So at one period after the first wave is emitted, the second wave is just starting to be emitted. So the wave front would be totally overlapping position 2. So that's why there's no, in this little area right in here between D and lambda A, there's no space in there. So once D stops, lambda A begins. So we can say that D plus lambda A equals lambda naught. Or if we want to rearrange that, we could say that lambda A is equal to lambda naught minus D. But we know that D from up here is equal to Vs times T, the speed of the source, times the period. So lambda A is equal to lambda naught minus Vs times T. But we also know, based on stuff we did in chapter 6, that T is equal to 1 over F. So the question is, which F is it? Is it the approaching F? Is it the receding F? Well, it's neither one of those. The period is how long it takes between emissions of waves. So that would be based on the original frequency, because that's not dependent on whether the thing is moving or not. So if we put that into our equation, we get lambda A is equal to lambda naught minus Vs over F naught. But we also know about the wave equation. So lambda is equal to, well, let's start from the beginning. V is equal to F lambda. So lambda is equal to V over F. Now, in this case, the V is the speed of the wave. This is the wave equation. It's not the object equation. So the speed V is our speed of the wave. So in the case of lambda A, the approaching frequency is equal to the speed of the wave divided by the approaching wavelength is equal to the speed of the wave divided by the frequency that is detected when the object is approaching. Same thing for lambda naught. It's V divided by F naught minus Vs divided by F naught. Conveniently, we have the same denominator in those fractions. So we can say V minus Vs over F naught is equal to V over Fa. We're starting to get pretty close here. Let's flip both sides, right? You can think of it as cross multiplying and then redividing. You can move the F naught over to the left-hand side and it goes on top, and move the V down to the right side and it goes on the bottom. It works out the same as simply flipping it. So Fa over V is equal to F naught over V minus Vs. This doesn't work if you have more than one fraction on either side, but because there's just one fraction on each side, you can do this. So we're almost done here. We could say this is Fa is equal to F naught times, we'll put this in brackets, V, because we're going to multiply by V on both sides to get that V over, divided by V minus Vs. And that is the equation for figuring out what the frequency of the sound is when the object is approaching. So you take the original frequency of the sound when it's not moving at all, and you multiply it by what's in this fraction. Now consider what's in the fraction. V divided by V minus Vs. So we've got two V's on top, and you might think that you want to simplify it, and I suppose that there are ways that you could, but it's not very simple, actually. So it's probably not considered simplifying. But consider what happens here. If you have a certain number on the top of the fraction. So right there you'll have a certain number. On the bottom, you should be able to say how the bottom value will compare to the top value. If you're going to take the same number you have on top and you're going to subtract something, you're obviously going to get a lower value. So this will be a lower value than this. So you get a high value on top and a low value on the bottom, which means that this value is greater than 1. You get a higher number divided by a lower number is greater than 1. So if we think about what we have here, we have the approaching frequency is equal to whatever the original frequency times a number greater than 1. So what that means is that the approaching frequency must be greater than the original frequency. That's why the frequency increases, or that is proof mathematically how the frequency increases when the object is approaching. Let's consider what happens when the object is receding. We don't have to go back and do the whole derivation all over again. Let's just look and see how it changes. So we'll head up to here. And now, consider our entire wave. Let me extend this out that way. So this is still lambda naught, but now this value here is lambda r. So when the object is receding, that's the wavelength that you're going to detect. So in this case, lambda r is equal to lambda naught plus d. So compare this to that. instead of subtracting d like we did in the first example, you're going to add d. That is the only difference. So if we look at that down here, we will add d over here instead of subtracting d. So if we look at lambda r, you're adding d. Lambda r, you're adding vst. Nothing else changes, just that one little part. So for lambda r is plus vs over f naught. Everything else stays the same, but instead of this being fa, it becomes fr, and this becomes plus. When we continue that all the way down, this is fr, this is a plus, this is fr, that becomes a plus, this is fr, and that is a plus. So instead of looking at this as two separate equations, we look at it as simply just one equation where you have a plus or a minus. When the frequency is receding, it's going to be added. When the frequency is approaching, it's going to be subtracted. So think about what happens to this fraction when it's receding. So v, we have a certain amount. And on the bottom, we have that certain amount v, plus we're going to add a little bit more. So this is going to be a higher number. And this one is going to be a lower number, which means that this fraction is less than 1, and therefore the receding frequency has to be less than the original frequency, and that's why the sound has a lower frequency. That's why the tone seems to go down. You can use this idea to mathematically remember or reason out whether you're adding or subtracting. So when we have this equation, f is equal to f naught times v over v plus or minus vs. I believe your formula on your formula sheet looks something like that. So here's the equation. You're looking at it going, oh, I can't remember if I'm supposed to add or subtract. You should be able to remember, or based on experience, know that when an object is approaching you, its frequency is higher, and when it's moving away, its frequency is lower. So if you're looking at for the approaching one, and you're trying to figure out whether you're adding or subtracting, when the object is approaching, f has to be larger than f naught. So that has to be larger. And if that's going to be larger, it means this has to be greater than 1. If that has to be greater than 1, then this value has to be larger than this value, which needs to be smaller. The only way that the value on the bottom can be smaller is if you subtract vs instead of adding it. So that's your hint for whether you add or subtract. I'll be perfectly honest with you. I don't have the adding and subtracting thing memorized. I start from this process each and every time. Because that way I know I'm never going to forget it. I know that, based on experience, I know what happens to frequencies when an object is coming towards me or moving away from me. So I use that knowledge that I'm not going to forget in order to figure out whether I have the equation done correctly or not. So let's put this to use in a relatively simple example. You have a siren with a frequency of 1200 hertz. What frequency is heard by someone on the side of the road if the siren is approaching them at 90 kilometers per hour? We're going to assume an air temperature of 20 degrees Celsius. So what are the things that we need to know? I want to find out what FA is, the approaching frequency. I know that V is the speed of the sound, which is 332 plus 0.59 t, which means 332 plus 0.59 times 20, which works out to be that's not it. 0.59 times 20 plus 332 is 343.8 meters per second. So that's the speed of the wave. The speed of the source is 90 kilometers per hour. It's been a long time maybe since you've done kinematics, but that is equal to 25 meters per second. I like to throw in the conversions just to make sure you keep thinking about it. And that's the only other thing that we need is our original frequency, which was 1200 hertz. So we're going to have our equation, FA is equal to F times V over V plus or minus Vs. Now I don't want you to do the plus or minus part. I want you to tell me which formula is correct here. And so, again, it's approaching. The frequency needs to increase. So V has to be greater than what's on the bottom, which means you need to subtract Vs to get a lower number on the bottom than you have on the top. From this point on, it's just a matter of plugging in numbers. 1200 times 343.8 divided by 343.8 minus 25. And right here I'm going to stop for a second because I want to point out two things. First of all, if you get V and Vs backwards, then you're going to get something really interesting. You're going to get 25 on top, and on the bottom you're going to get negative 300 and something, which means that your entire answer is going to be negative. Is it possible to have a negative frequency? No. No, the frequency is how many times a second something happens. Something can't happen a negative amount of times. So getting a negative answer doesn't make any sense. And that will pretty much always be true as long as your object is going at subsonic speed. As long as it's not eclipsing the speed of sound, you would end up with a negative value, unless you also compounded the mistake by adding instead of subtracting here. So that's one thing. The second thing I want to point out is that if the smaller the value for Vs, right here, the smaller that is, the less of an effect it's going to have on that 343.8. So as I'm walking towards the computer right now and speaking, you're probably not noticing a difference in my pitch because I'm only walking at about half a meter per second. So adding a half meter in there is not going to make much of a difference. That fraction is going to be still pretty close to 1. And that's why you don't notice, that's why this equation doesn't work for light. So we don't notice like we have a yellow car coming towards us and the frequency of the light goes up, and instead of it being yellow, it might look green. Yes, that does actually happen, but not with cars. It happens with stars that are in other galaxies, where the star's light shifts a little bit, and we can definitely notice it there. But that's because those galaxies are moving away from us at 10%, 5%, 20% of the speed of light, and so that's when it makes a difference. The rule of thumb that I like to use is that the speeds have to be at least 5% of the speed of the wave in order to notice much of a difference. So you probably aren't going to notice a huge difference as a car is kind of rolling towards you on your street going maybe 10 kilometers an hour. So let's finish up the calculation here. It's just a matter of plugging numbers in. You might have already done that while I was talking away here. 343.8 divided by 318.8 gives you 1.078. So the frequency will go up by 7.8%, which results in a value of about 1294 hertz. So just to give you an impression, I can create a 1200 hertz tone here on my GLX, and then I can show you a 1294 hertz tone. Now remember, this is something going, I'm not exactly sure what this child is doing standing on the side of a road with a car coming down it at 90 kilometers an hour, but in any event, no children were harmed in the making of this question. So let me type in 1200 here, and there's a 1200 hertz tone. This is 1293. So what you would hear is this as it was approaching you, this if it stopped right in front of you. If we were to find out what it would be like once it's past the child, once this has passed the child, all we would really need to do is put in a plus sign over here and add that 25 instead. And a quick calculation there, 343.8 plus 25 is 368.8. Which gives about 1119 hertz if receding. So if I plug in to my GLX here 1119, we get this. So the siren would sound like this coming towards you, and this going away. So you would hear it as so you'd hear. Now, not many sirens are that monotone. There's a reason that it's not just one tone. It gets your attention a little bit more when it's fluctuating its frequency. But in any event, there are lots of questions in your hit list to practice these. And this is a question that I've asked before on some quizzes. I think I'd like to give you a little bit more time to work on this. Once you've done all of your other Doppler effect questions, I would like you to try this one. It's not as simple as it might originally seem, but it's worth giving it a shot. There's lots. If this was a quiz, a test question, and again, I have asked this as a test question, out of 4, there's probably 2 marks out of those 4 that are actually pretty simple to get. A third mark requires a little bit of thinking, but maybe you might have some mistakes in your thought process, but enough to get you another mark. The 4th mark is probably a little bit more difficult. So try this one, and we'll see how it goes. And again, I can take a look at it in class tomorrow.